Hello students, today we are going to start the another topic of chemical equilibrium is relation between the Kp and Kc. So what is the relation between the equilibrium constant in partial pressure condition and concentration condition? So we are going to discuss it. In previous lecture we discussed some terms about the chemical equilibrium, mostly extent of reaction. Okay, how we decide the reaction is more favored towards the product side or backward side, we will well understand about this. So today we are going to start, the topic is relationship between the Kp and Kc. For that we consider a simple reaction is A plus B, which is converts into C plus D. So small ab's are the reaction coefficient, CD also reaction coefficient. You familiar with this? So according to law of chemical equilibrium, we find out the relation, the Kc. Kc is the equilibrium constant and it is the ratio of product of concentration with rise proper power upon product of reactants with rise their power. So using this equation we can write Kc is equal to concentration of C with power C into concentration of T with power D. So there is a product side, so product upon reactant we get the first equation. If we assume that here the Kc is given in the form of concentration, here we relate the Kc and Kp each other. So for Kp, the reaction condition is a gaseous state. And if there is a gaseous state, means reactants and products are react together, and when reactants are react together, product is formed, both are in a gaseous state. And you know, if there is a gas, we assuming that both the gases are ideal. So for ideal gas, the equation is equal to PV is equal to nRT. So it is the first equation, you familiar with this. So using this equation we can find the P. So P is equal to, this V goes here denominator, and here N upon V RT is the equation, and using this it is same as a P is equal to CRT, because C is the concentration, and concentration find the number of moles upon volume, and here NV, N is the number of moles, V is the volume. So these are considered as a C because this is the concentration. So we get P is equal to CRT, it is the equation number 3rd. In next what? We substitute this equation number 3 into equation number 1, because here in the terms are in the concentration form. Here we want to convert into partial pressure form. Okay, so partial pressure express the concentration, and here simple concentration express the means gram per liter, and here in the form of bar which express the concentration. So when we put this value equation number 3 into equation number 1, so here what is the equation number 3rd? It is a P is equal to CRT. So using this equation we get the C. What is the C? C is the concentration, and concentration is equal to PRT. P upon RT is the concentration, and we replace the concentration by PRT. So here in equation number 1st we place the values of this. So what is the equation 3rd? Here is the C is the concentration. So we add P upon RT, so we get PC upon RT. The power is C. PD upon RT, the power is D for the products. For the reactants, PA because we put this value PRT with power A, and PB upon RT with power B. So we add the equation 3 into equation 1. Up to this we get the new equation is the equation number 4. Come to on the another side, where partial pressures of the species are made as a dimensionless, so by dividing the pressure by 1. So here the partial pressure is in the dimension, this is the in the form of dimension. We made it the dimensionless by the dividing this species by pressure 1. So here we get the answer. So when there is a dimensional less, so dimensions are removed, so we simply get what? PC with power C, with PD with power D, PA with power A, PB is equal to, there is a RT is remain. So here 1 upon RD C plus D 1 upon RT A plus B, because here is a C and D is power, here A and B, and RT is there. So we consider this species as a Kp. It is a Kp. Okay, concentration Kc is equal to, this is a Kp. The RT which is here, which is considered as a common, and these two are A plus B. So A plus B minus C plus D. So A plus B and C plus D are the number of moles in a reactants as well as a product. So we get the number of moles of reactant minus number of moles of product. That means there is a change in number of moles. So we simple this consider as a delta N. The value is negative. The value is negative because it is a reactant minus product. So that's why here sign is negative. Okay, so we simple Kc is equal to Kp, which is coming from this species, RT is there as it is, we take consider as a common, and change in concentration means this value. So when we going to calculate Kp, so Kp comes out, so Kc is here, so Kc RT, we get the same equation, equation number 6. So we get the value of Kp. It is equal to Kc into RT with power change in concentration. Okay, change in concentration. So delta N is the change in concentration, means number of moles changes between the reactants and products. So Kp, Kc are dimensionless, RT also dimensionless, there is no dimension. That means Kp is equal to Kc into 0.0831, this is the value of R. This is the value of R is the universal gas constant. Okay, and it is the value of R is given. It is a universal gas constant value 0.0831 per Kelvin into T delta N. So this is the relationship between the Kp and Kc. So if we have the value of Kc, we can calculate the value of Kp, or if we have the value of Kc, we can calculate the value of, if we have the value of Kp, we can calculate value of Kc. So we can solve the problem which is based on it. So it is the first topic, which is the relationship between the Kp and Kc. The next point is molecular interpretation of equilibrium constant. We are going to discuss it. Okay, the second point is molecular interpretation of equilibrium constant. So you know the equilibrium constant indicates the specific composition of reactant and product when reaction is reaches to the equilibrium point. So the significance of equilibrium point is the temperature dependent, it is the function of the temperature. So using Boltzmann distribution constant or with this Boltzmann distribution concept, we can find out the molecular interpretation of equilibrium constant. So the molecular reactant is over the available in the energy states. So here two diagrams are given to you. A and B are two species. So simple here reaction we consider A converts into B. So A is reactant, B is the product. So here in first case the population versus energy states are plotted, and here A which is represented as a dotted and B which is represented as a thin line. So basically both having the same concentration, because they has a similar densities when it reaches to the equilibrium point. So how we predict or interpret it, the reaction is favored to the product side or reactant side, more will be formed here. How we conclude or understand the product form more favorably or reactant remains more favorably, means reaction is backward direction or forward direction. So for that we consider if the both the reactant and product has same energy states, that time the species which attain the lower energy state. So you can see here the last energy state of the A, and this here is the last energy state of B. That means here what happened, B reaches at the most lower energy state at the equilibrium, means in given reaction B is more dominate as on the A, that means B is the product. B is the product. So product will form here more dominantly over on reactant. So this reaction is favored to the product side. But in second case, this is another type of distribution, Boltzmann distribution. What happened here? Here energy states are given. So the very higher densities here means A has greater density as compared to B. But no doubt B has lower energy state as compared to A, but you can see here the number of energy states are more here as compared to B. That means here the concentration of B is more, sorry, the concentration of A is more as compared to B. That means A is dominated to the B. So A form more favoredly as compared to B. That means A is reactant. So reactant form more dominantly over on B. That means reaction is favored to the reverse direction. So the reaction is reverse reaction, so more reverse reaction is favored. So using this Boltzmann distribution concept, we can easily understand how the molecular interpretation of equilibrium constant means molecular states we consider here, and using molecular state at the equilibrium point we can easily understand the reaction is favored at which direction, means backward direction or forward direction. So we already have the equation delta G naught is equal to minus RT ln K. So we can using this equation find out the K here. So ln K is equal to this comes here. So with the minus sign, that means minus delta Z naught upon RT is here. So we put this value, and already we have the equation for the Gibbs free energy at a standard. So standard Gibbs free energy, it is the standard enthalpy minus T delta or standard entropy. So using this equation we put the value of this ln K, because it is equal to delta G naught upon RT, put is here. So ln K is equal to, we have this value, so delta G is equal to this, so we put this values here. So if we put value here, so minus delta H naught upon RT plus delta S naught upon R, because if we consider RT is here, TT is cancelled, so what remain? Delta S naught upon R. This is the equation. So K is equal to e raised to delta H, here is the naught upon R, so it is a function of T, so we can T is here, delta H naught upon RT, delta S naught upon R. So delta S naught means it is a standard entropy, delta H naught means it is a standard enthalpy. So using standard conditions, enthalpy and entropy, we can find out the K. K is the equilibrium constant. So in molecular state we can find out the K. So this is very important point to understand how reaction is favored. It is a backward or reverse reaction, means forward or backward reaction. So next point we are going to discuss here the responses of equilibria to condition, means we are going to discuss in detail. So next point is the response of equilibria to condition. Equilibria to condition. Okay, what is the meaning? When anything, means any reaction which is reaches to the equilibrium point, so when it reaches to the equilibrium point, there is a change in the concentration is stopped, means concentration remains unchanged. So when concentration is, how much time of concentration is unchanged? Up to we can apply the stress on it. If we disturb the equilibrium condition, means by changing the concentration, by changing the pressure till the condition remains unchanged. Unchanged condition is there. So when we apply the any external disturbance, means we change the concentration or sometimes we change the pressure. So if we change the concentration, we change the pressure, that means what will happen there, there is a introduction of the stress on the condition. And when there is a stress is applied on the condition, stress means when we do the change in concentration, when we do the change in pressure, that are the conditions which are changed. So when the conditions are changed, how equilibrium is responses. So when we apply the stress on equilibrium condition, the equilibrium condition try to shift to reduce their stress. So equilibrium condition to change their equilibrium states and try to reduce the stress which is applied. If the sufficient time is available, it is possible to attain the new equilibrium state. So one equilibrium state is shifted into another equilibrium state. It is possible if time is available when we apply the disturbance condition, disturbing condition, that means apply the concentration, when I apply the change in temperature, when we change in concentration, change in pressures, these are the conditions which are response to the equilibrium constant. So this thing is established by Lee-Chancellor. So Lee-Chancellor principle is introduced when we apply these certain conditions on equilibrium at particular time is available, then it is possible the one equilibrium condition shifted to the another equilibrium condition, and it is the Lee-Chancellor principle. So there are three conditions we are change here. First is change in concentration, change in concentration. Second, change in pressure. If we change the pressure, what happen? And third is change in temperature. So on equilibrium, if we do, one of the thing is here how equilibrium is shifted or how equilibrium is responses to the conditions, and this is the point of discussion. So the responses of equilibria to the conditions. So when we change the condition, so here we are going to discuss the first condition is equilibria to the concentrations. Okay, so you know the yield of the product is by the removing of yield of the product is by removing the product or by adding the reactant. So if you want to condition, suppose A converts into B is the reaction. Suppose we consider what? A converts into B, or suppose we consider A plus B gives C. A plus B gives C, and A and B is the reactant, C is the product. So how we obtain the yield of the product? So simply from this equilibrium point, if we remove the reactant, so remaining is product, or simply we just remove the product. म्हणजे एक रिॲक्शन आहे आणि रिॲक्शनमधनं आपल्याला यील्ड काढायची असेल तर यील्ड कशी काढणार की 1 ग्रॅम, सपोज हा 1 ग्रॅम घेतला, हा 1 ग्रॅम घेतला आणि इथं आपल्याला हा 1च ग्रॅम भेटला, यील्ड किती मिळाली? 50% भेटली. का? कारण की याच्यामधनं हा किती होता? 1. सो वी निग्लेक्ट द concentration, we neglect the amount of reactant, so the remaining amount is the yield of the reaction. So for that we consider simple reaction, and here we are going to discuss the point is change in concentration. Change in concentration. Suppose we consider reaction H2 plus N2 gives NH3. H2 plus N2 gives NH3, and you know the reaction how to balance? Thrice H2s are required and twice NH3 is formed. So this is a simple the formation of ammonia by which process? You familiar with this one? It is a Haber process which is used to manufacture of ammonia. So here in first case what we do here, suppose we add, so adding of reactant, suppose we add the reactant, more reactant, in means change in concentration means what? If this reaction is happen, this is the products reactants, suppose we add one of the reactant more. So we increase the concentration. When increase the concentration, so what happen in equilibrium? So reaction favor in equilibrium state. So here, according to equilibrium constant, Q is equal to concentration of NH3 upon concentration of N2 upon concentration of H2. We already have this. Suppose what happen if we add the concentration of H2 more, if we add the concentration of, and at equilibrium, you know Q is equal to K. So at equilibrium Q is equal to K, and we can calculate Q using this. So concentration of NH3, it is the condition at equilibrium. So after that, suppose you think if we change the concentration of reactant, means change the concentration of N2 or change the concentration of H2. So what happen if you add the more H2 is here, what we increase the amount of H2, so the concentration at denominator is increases. If concentration at denominator is increases, then the value of value of Q goes decreases. Value of Q goes decreases because this value is increases. If this value is, suppose here, basically here 1 is there. Suppose you consider the ratio is 1. If you increase this concentration, the value is goes decreases. So Q is less than K because K is constant. So change in quotient is decreases. So if the value of Q is decreases, so we simple what? K is greater than Q. K is greater than Q. That means reaction proceed to the right side. Reaction proceed to the right side. That means the reaction is more favored to the formation of product. More favored to the formation of the product. So reactant side ला अजून ऍड केलं का रिएक्शन कुठं फेवरड टू द राइट साइड. राइट साइड म्हणजे काय असणार आहे? फॉर्मेशन ऑफ द प्रोडक्ट. सेकंड कंडिशन, बाय द रिमूव्हिंग ऑफ द substance also favor the reaction. Removing of the substance means if we remove the substances here, which if we remove some NH3, then what happen? If we remove the NH3, again use this condition. So here the concentration is decreases at numerator. So if concentration decreases here, the value of this denominator is more as compared to numerator. So the value is more here, less here. So again Q is decreases, and again Q is decreases. That means again we have K is greater than Q. म्हणजे इथली जर व्हॅल्यू अमाऊंट कमी केली तर इथलं कॉन्सन्ट्रेशन कमी होणार प्रोडक्टचं आणि याचं कॉन्सन्ट्रेशन जास्त असणार. आणि जर आपण केची व्हॅल्यू काढली तर ती केपेक्षा कमी होणार. इथली जर ॲडिशन केली तर याची कॉन्सन्ट्रेशन वाढणार, याच्यापेक्षा अजून केची व्हॅल्यू काय होणार? कमी होणार. ओके. सो इन ऑल केसेस, की पहिल्या केसमध्ये इथं आपण ॲडिशन केली, डिनॉमिनेटरचे कॉन्सन्ट्रेशन वाढलं, इथं आपण कमी केलं तरी डिनॉमिनेटरचं कॉन्सन्ट्रेशन जास्त असणार. म्हणजे दोघी कंडिशन्समध्ये होणार काय की क्यूची व्हॅल्यू कमी होणार, डिक्रीज होणार. इफ क्यू इज डिक्रीजेस दॅन के, द रिॲक्शन इज फेवर्ड टू द राईट साईड, and if Q is greater than K, reaction favors at the back side. So reaction is favored at the right side. So in both the cases, reaction always shifted on right means forward to the formation of more and more product. So in next lecture we discuss about the product, means responses of when change in pressure and change in temperature. So we stop here.